Let us consider a uniform electric field with 2 points A and B. Now let's say that the work done in moving a charge from A to B is W along this line. Let's call this value W. Right? Now let's go along an alternate path as such. Now let's say that the work done in moving from point A to, let's call this point B. Let's actually change it a little bit. Right. Now let's call this point P and this point Q. And now the work done in moving the charge from A to P would be W1. From P to Q is W2, and from Q to B is W3. Now we know that in an electrostatic field or in an electric field, the work done does not depend on the actual path followed by the object or the charge. It just depends on the displacement between the final point and the initial point. So now what this tells us is that the work done while traveling the shortest path, which is directly from A to B, which is W, this is going to be equal to the work done in traveling along the longer path. So W is going to be equal to W1 plus W2 plus W3. Let's revisit the definition of potential difference. Potential difference, which is V, is defined as the work done in moving a charge. So if V is equal to W by Q, that tells us that W is equal to VQ, right? So now we can substitute the W's here with VQ's. So this W would become VQ. W1 would become V1Q. And you would do the same thing for W2 and W3. So this would be V2Q and V3Q. Now the Q's are common on both sides, so we cancel them out. And now what that means is that the total potential difference between 2 points is the sum of all elementary potential differences, regardless of what the path taken is. So V is going to be equal to V1 plus V2 plus V3. So now let's keep this in mind. After that, let's look at Ohm's law, which states that the potential difference is equal to the current multiplied by the resistance. We can use this law in a circuit which has resistors connected in series, which was the purpose of this video. So now if we have 3 resistors connected in series as such, this R1, R2 and R3. So now we know that the current flowing through each resistor is the same, because if the current were not the same, then the charges would accumulate in one place, and the wire itself would become charged, which is not something that we see. The total charge of a wire is 0. So what? So we can conclude that I1 is equal to I2, which is equal to I3. And since all three terms are equal, let's just call all the three i's, I1, I2, and I3, just I, right? And now we also figured out that the total voltage is V1 plus V2 plus V3. Now let's add three voltages, or the three potential differences. So this is going to be equal to V, right? So now Ohm's law says that this V1 can instead be written as I1 R1. So we can write this as I1 R1 plus I2 R2 plus I3 R3 is equal to IR. And now this equation says that all three i's are the same, so I'm just going to remove the subscript from the i's. Oh, that's too bad. So IR1 plus IR2 is equal plus IR3 is equal to IR. So now we see that the i's are common on both sides, so we eliminate the i's, and that gives us R1 plus R2 plus R3 is equal to R. R is the total resistance of the entire circuit. R1, R2 and R3 are the individual resistances of each resistor. Here I use 3 resistors, but one can use as many as one needs. So this is the formula for resistors in series. Thank you.